Another method of finding the determinant of bigger matrices is through Chio'S condensation. This video will showcase how Chio'S pivotal condensation is used. Welcome to Numerical Solutions to CE Problems. We will use the same matrix when we discuss Laplace cofactor expansion in order for you to compare the length of each procedure. There is a mandatory condition for Chio'S pivotal condensation method, and that is the element must be positive 1. From the matrix, there are several ones. There is 1 in element 2, 2, 1, 3. There is also element 3, 5, element 4, 4, and element 5, 2. With so many options, we consider 1 from element 4, 4. Having a matrix in order 5, we need to reduce it into 4 by 4. With element 4, 4 as the pivot element, we highlight the 4th column and the 4th row. The remaining elements in the matrix will be outlined as shown. Where the matrix has a scalar of -1 raised to the row and column indices. Those are 4 and 4. Now instead of smaller determinants, we check the reflected factors. For element 1, 1, the reflected factors are 0 and 5. Multiply these two and subtract it from the element. For element 2, 1, which is -1, the reflected factors are 0 and 3. So the new element becomes -1 minus 0 times 3. For element 1, 3, the reflected factors are 0 and 2. So the new element 1, 3 is 2 minus 0 times 2. The last element in the first column is -2. Then the reflected factors to be subtracted are 0 and 3. The second column from element 1, 2 has reflected factors as -2 and 5. Going down the same column, 1 is subtracted by the reflected factors of -2 and 3. Element 3, 2 is subtracted by -2 times 2. Then the last row of column 2 has the reflected factors of -2 and 3. Continue to the third column, first row with element 1. This is subtracted by -1 times 5. The element below it will be subtracted by -1 times 3. Further down the column, for element 3, 3, the reflected factors are -1 and 2. To finish the third column, the last row has element -1 and be subtracted by -1 times 3. Column 4 is where we take the factors, so we move to the fifth column. From the first row, we subtract 3 times 5 from -1. The next element below it has the reflected factors 3 and 3. Then the third row from that column is subtracted by 3 times 2. Then the last element on the column and row is 4. This is subtracted by the reflected factors 3 times 3. Work on the products and differences and simplify the matrix. Now we got a reduced matrix of order 4. we still can't use any shortcut methods as the matrix is still big. Another problem is there's no positive 1 element in the matrix anymore. To be able to come up with 1, take a look at the second row. It has an element valued at -1. We can extract -1 from the row to have a positive 1 element, and we can move on with the procedure. The matrix would have a prefix of -1, which we extracted, and the elements show 1, -7, -5, and +11. With the +1 already available, we can reduce matrix G into order 3 by using pivot element A to 1. We generate the factors by highlighting the row and column of pivot element A to 1. The remaining elements are then outlined where there is an additional prefix of a -1 raised to the indices of the row and column 2 plus 1. For the process of element 1, 1, we subtract 3 times -7. The second element in the column is subtracted by 2 times -7. The last element in column 1 is subtracted by -2 times -7. On to the second column. Start with the first row, then note that the reflected factors are 3 and -5. The new element 2, 2 is subtracted by 2 times -5. Finish the second column and have element 3, 2 be subtracted by -2 times -5. For the last column, start at the top row and subtract 3 times 11 from -16. The next element below has -5 decreased by 2 times 11. The last element has another -5 subtracted by -2 times 11. Simplify all elements in the matrix. After another round of condensation, matrix G turned to be 3 by 3, which we can solve through Sarrus rule. Mirror the first two columns and take diagonals and anti-diagonals. The first has 33 times 12 times 17, which is 6,732. The next diagonal has 21 by -27 by -7, which results to 3,969. The third diagonal has -49 times 17 times -8, giving 6,664. The anti-diagonals are computed as first -7 times 12 times -49, and that is 4,116. The second anti-diagonal has -8 times -27 times 33, and that is 7,128. The last secondary diagonal has 17 by 17 by 21, which is equal to 6,069. Place all these to have the determinant of G as 6,732 plus 3,969 plus 6,664 minus the quantity of 4,116 plus 7,128 plus 6,069, resulting to the determinant of G as 52.